Okay, this video is about k-median problem. So again, in the starters folder, click on k-median. Okay, so if you'll remember this problem, we're trying to locate 5 factories for wind turbines, and we have 100 possible locations that we're considering, and then ultimately these 5 factories that we build are going to serve 1,000 different demand points. So this may be something like what a solution could be. Okay, so let's define some of this information. So K is 5, that's how many factories we want. But the number of factory locations, or candidate factory locations, is, we've got 100 of them, and let's number them. This is the candidate factory locations. They'll be numbered 0, 1, 2, and so on, all the way to 99. And I guess maybe here I'll also specify this is the desired number of factories. And then the demand points, we'll also just go ahead and number them. They'll be numbered 0 through 999. Okay, and this is just for convenience. Maybe it would be better if they were named, but for purposes of this exercise, we're just going to suppose everything's numbered. Okay, so that defines our factory locations, demand points, and K. And just for this exercise, it's just going to make things easier if we just work with some random data. So I'm going to just suppose that each of these factories is located by an X and Y coordinates. And we're just going to pick these X and Y coordinates at random between 0 and 1. So to get random numbers in Python, I'll import this random package. And the factory locations, they're specifically their X coordinates. I'm just going to say random.random. So this will give me a number between 0 and 1. Maybe just to illustrate that, random.random gives me 0.93, 0.88, 0.006, and so on. Okay. This gives a number, or a pseudo-random number, I should say. Pseudo-random number from 0 to 1. And it may be something like that. I don't remember. A close interval. But for all practical purposes, it doesn't make a difference. Okay. So these factory location X coordinates, I'll draw like that. This will be for all I in a set of factories. And I'll do the same thing for the Y coordinates. So the Y coordinate will again be just a random number between 0 and 1. Okay. So I've essentially drawn X and Y coordinates at random for 100 different factory locations. So let's draw that. So I'm going to use this matplotlib package, matplotlib, and I'm going to get pyplot. So we'll import it as plt plot. And I'm going to do a scatter plot. And so I can just, the first argument can be just all of the X coordinates. And then the second argument is just a list of all of the Y coordinates. So if we just go ahead and show that. Yep, PLT. Okay. So those are my 100 random candidate locations. Now, just to clean things up a little bit, I'll give this a title. So these are the candidate sites. Put the title up here. And the way that PyPlot is picking the range for the X's and the range for the Y's is based just on the data. And so since the data is pretty well scattered throughout here, it's just choosing to go from 0 to 1. But if I were to print just one of these locations or 5 of these locations, like we'll do later, it'll probably kind of crop the image or crop the plot to fit those 5 points. And so then I may not get this full picture going from 0 to 1. So to force it to use the range going fully from 0 to 1, I'll do this. Limit and the Y limits will both be 0 and 1. I think it probably won't change the picture here, but it will change the picture later on. Okay. So there I have my 100 candidate locations for the factories. And then I'll do the same exact thing for the demand points. So maybe I'll just copy this. Instead of the factory locations, I want demand locations. I want X and Y coordinates, and I want this for all J in a set of demand points for both of them. Giving me 1,000 demand points. And then I'll just draw them in the exact same way. So here I want demand points. These are no longer candidate sites, these are endpoints. That. Okay, so you can see a lot more points. More densely packed. Okay. So for right now, let's define this cost of assigning factory I to cover demand point J. And I'll just say the cost is 1. This is for all I in factory candidate locations and for all J in demand points. And okay. So I want this cost to be somehow related to the distance between the factory and the demand point. So an easy way to do this is to just refer to the rectilinear distance, which, if you recall, the rectilinear distance between 2 points is the absolute value of the difference of the x's plus the absolute value of the difference of the y's. So this could be like x1 is x2 plus absolute value in the difference in the y coordinates. So this is what I'll return. So I just need to specify the arguments here, x1, y1, x2, y2. So this is the distance, or the rectilinear distance the point x1, y1, and the other point x2, y2. So one of these could be a factory location, the other one could be a demand point. Okay, so I'm going to use this to define my costs. I'm just going to say that the cost is that rectilinear distance between the factory and the demand point. And so let's say the factory location x coordinate for I and the factory location y coordinate for I. That defines my first x and y. And then I'll just do the same thing for the demand point. It's x coordinate and it's okay. I think that's good. Maybe I'll put some spaces in here to make this a little more legible. Okay, so this defines this function for rectilinear distance, and then this creates this cost dictionary for all choices of I and j. Okay, so we'll rerun some of this if we use Chebyshev distance or Euclidean distance, but I won't do that quite yet. So let's go ahead and build the model. So I guess, as usual, import Gurobi. Create my model. We'll create these x variables. So x variables are the assignment variables. So we have one of these variables for every choice of I, which is the set of factories, and every choice of j, which is the set of demand points. And I think we have our choice. We could define these as continuous or as binary. I'll just leave them as continuous. And maybe I should also mention, by default, Gurobi will assume that any variable you define should be non-negative. I don't need to necessarily specify that. Okay, we'll do the same thing for y variables. So I will have these variables, and I want these for every factory. Now these, I think it is very important that these are binary. So try that. Okay. All right, next I'll define the objective. And again, the first argument is what I'm optimizing. The second argument is this objective sense, which is minimized. And so what I'm minimizing is that sum of the Cij, Xij's. So Ij for I in factories and for j in demand points. And I need to multiply that by that cost. That. So using that rectilinear distance from above. Okay, I think that's good for the objective. Run that. Okay. My first constraint is that I pick k of those factory sites. So this is the k and k median. So m dot add constraint, and it's just a single constraint, so there's no s here. So I want to pick exactly k factories. So I want to sum over the y variables. So I could say sum yi for I in factories. This would work. There's also another way I could write this. If you want to just sum all of the variables of a given type, like sum all of the y variables, there's a shortcut. I can just write it like that. Okay. So each one of these demand points j should be covered or assigned. So I have a lot of constraints here, 1,000 of them, one for each demand point. So I want to make sure that they're fully assigned to a factory. This should be for every j in the set of demand points. And I want to sum those xij variables. And I want to sum over all of the different factories. So all of the factories that could service this demand point. So for I. Okay. And then I also want to make sure that if a factory isn't built, then it doesn't service any demand. So again, I have a lot of constraints. And this is actually going to be not just one constraint, not just 1,000 constraints. This is going to be 100,000 constraints. This is for every choice of I and every choice of J. So these constraints look like I want to impose this for every I and for every J. Okay. And I caution you not to run this cell like this, because it's going to print the name of this constraint for every I and every J. So it's going to print 100,000 different things. So to avoid that, I just do end.update. Okay, I think that looks good. I'll run that. Okay. So if I wanted to, I just go ahead and start solving. And you'll see that I have those 100 integer, let's say binary variables, those are the y's. And then I have 100,000 of those x variables, which are continuous. And depending on the instance, this may solve quite quickly. So in this case, it took 20 seconds. I've seen cases where this will run for minutes and not even solve the LP relaxation. So to avoid that, a good thing for this instance is to tell Gurobi not just to try primal simplex and dual simplex, but also to force it to use an interior point method or a barrier method. So for that, we can do m.params.method. And I wanted to use the third option, which is the concurrent method, which on different processors on your computer, it'll try primal simplex on one of them, dual simplex on another, and barrier method on another. I think if you have at least, well, 3 cores, I think probably 4 is more likely. If you have at least 4 cores, it'll run these all kind of simultaneously. And whichever one of these LP methods solves first, it'll just stop the others that are running, terminate. Okay, so I was curious to see how long that would take instead of that 20 seconds. I should probably reset the model. So that'll just kind of remove all of the solve status information. Because otherwise, if I were to solve this again, it would immediately just return the solution that I had before. So to not give this any head start, I'll just reset the solve status. Then I'll force it to use concurrent, and then I'll optimize again. And let's see. This may end up being no faster. Let's see. Okay, so it was a little faster. It was about only 10 seconds as opposed to 20 seconds. But I think this is more robust. I think it consistently will solve in something like 10 seconds or less. But if you were to not set this, it may take minutes. Okay, so this is a nice trick to have in your belt to be able to force Gurobi to use this concurrent method. Okay, so now that we've solved, we can get this solution. So the set of medians, this k-median problem, these are our factory locations. So this is the set of all I for I in a set of factories for which I variable equals 1. Again, because of floating point considerations, we shouldn't just ask if this variable value equals 1. We should just ask if it's at least some large enough number. So I use 0.5, you could use 0.9 or 0.99. Any of those would ultimately give you the same answer. So maybe I'll just print what those are. So of our medians, our factory locations were 0, 1, 2, 3, all the way to 99, and these were the 5 that it chose. And then if I want to plot this, I'll need to get what their x and y coordinates are. So coordinates of these 5 factories are factory location of x, I, or I in those medians that we've just defined. That'll give us the x coordinates, and then we'll also need the y coordinates for those 5. And then we can draw that. So we'll do our scatter plot. We're going to plot the medians x coordinates and the medians. Do this. And so this is saying those are the locations, those 5 factories that I should build. And you'll see that the scale here, these axes, it's no longer going from 0 to 1. So matplotlib is kind of cropping this image around those 5 points. So if I wanted to see what this would really look like in my 0, 1 cube, I should do that. And this looks a little more reasonable. I mean, you would think you wouldn't want to put a factory at the corner of your set of points. So it should be a little bit in the interior. Okay, and maybe I'll also give this plot a title. So instead of factory locations or candidate sites, I'll say best. Okay. So that tells me where the factories are located, but it doesn't tell me how these demand points have been assigned to the factories. So what I could do is say, for each one of these medians, so maybe this median, I'll look at what are all of the points, demand points that are assigned to it. So let's see. So the way I'm going to do this is I'm going to loop through medians going from median 0, median 1, median 2, median 3, all the way to the, I guess, the 5th one in our list, which would be numbered as median 4. So this would be here are 5 medians. So same as before. Now I'll look at who is assigned to each of these medians. This is the set of all domain points j. If variable is at least 0.5, and it should be binary, I think. But okay, so we have the set of all domain points j. If that xij is at least 0.5, then we'll say that that j is assigned to I. Okay, maybe I could just print out as this many demand points assigned to it. I can just look at the length of that list. Okay, so the first one has 175 of the 1,000 demand points assigned to it. The next one has 204, 181, 220, 220. Okay. All right, so I want to draw, let's say for the first median, I want to draw these 175 points. So I'll need to know their x and y coordinates. So coordinates are going to be demand x for j in assigned. And the y coordinates of these assigned points. And I can plot them. Remember in this plot function, the first thing is what are the x coordinates, and the second thing is what are the y coordinates. So I could do this. That works. Maybe I should add a couple more things to this. So I'll just force it, just to double check, I'll force it to go from 0 to 1. And I'll give it a title. Okay. Okay. So probably pretty clear. All of these red points are assigned to this factory. All these blue points are assigned to this factory, and so on. And if you look at the shapes of these kind of service regions, you'll see that they have kind of a diamond-like shape. So specifically the purple one that's in the middle, it looks kind of like a diamond, which if you think about rectilinear distances, this maybe shouldn't surprise you. So if you were to pick like the point in the center of this diamond, the set of all points that are within a certain radius or distance to it form a diamond shape. So I think we may have seen this in a previous lecture. So if we had more factories and more demand points, probably these kind of cells in this picture, a lot of the interior cells would probably look diamond shaped like this. Okay. All right, so this is, I think this essentially does it for this problem if we're working with rectilinear distances. But maybe out of curiosity, let's just see if these pictures would look any different if we used a different distance measure. So let's define something for the Chebyshev distance. And I'll pass x1, y1, x2, y2 as arguments. And if you remember the Chebyshev distance, it was the max of these two things. So either the distance in the x dimension or the distance in the y dimension, whichever one of those is bigger, that defines the Chebyshev distance. Do the same sort of thing, but now do Chebyshev distance. Comment that out. I think that should work. So basically, I'll just rerun all of these cells. Now, granted, that will make the candidate sites and the demand points a little different, but it's okay. They're all random anyway. So I'll restart and run all. Let's see what happens. Okay. So of course, the instance is different, but the locations of these centers look a little different than before. And you'll see that the shapes of these cells in this picture, the kind of the service regions, are not quite like a diamond like they were before. They're closer to a square. And again, this is kind of unsurprising if you're familiar with Chebyshev distance. that if you look at like the center of this, let's say the green region, and you look at all of the points that are within a unit distance from it, that forms a square around that point. So you may also recall that from the previous lecture. Okay. All right, so let's do the same thing, but instead of working with rectilinear Chebyshev distance, let's use Euclidean distance. Maybe I'll just copy this and edit it. So use Euclidean distance. And so I'll just have to redefine this thing. So this should be, we're looking with Euclidean distances, we're going to need the square root. So I think square root is not a function that's immediately usable in Python. We have to import this math package or math library. So we'll do math.square root of something. That something is going to be, the x1 minus x2 squared plus the same thing for the y's. I need to square both of these terms. And you may be tempted to write caret 2 on each of these, but this is actually a different operation in Python. It's not squaring. So actually to square it, we should do star star 2. I think that should work. So let's go ahead and run this all again. Well, we have a very similar to the kind of those diamond-shaped regions. Yeah, I think maybe this has less to do with Euclidean distance and more to do with just if you're looking at a point, like a demand point in this region, which node are you going to assign it to? You're going to assign it to whichever one is closest. And so it ends up just being that you get these kind of straight lines between these regions. I think this is like what you'd see in Voronoi diagrams. Okay. So I think of these different distance measures, I think rectilinear is probably the one that's closest to the actual distance that you would be traveling in practice in a road network. So Euclidean distance is maybe a little too much to ask for, that you can kind of just move in a straight line between any 2 points. So I think that's not super practical. Chebyshev distance, I think, is also not super practical. But if you think about roads in Oklahoma that are often based off of a grid pattern, rectilinear distance is actually pretty close to what you'd be driving. So I think a lot of transportation logistics type companies will use this in their a lot of their coding applications. Of course, they won't be using random 0, 1 point or random points in the 0, 1 square, but they would be working with latitude and longitude coordinates. But the same sort of thing can be done. So I'll run this one more time for those rectilinear distances, because I think this is probably the most appropriate distance measure of the 3 that we talked about, if you're not using actual road distances. Taking a little bit of time to solve. But I guess if we're working with 100,000 variables, we shouldn't be. asking for too much. Okay.